Hi everyone. So last time I was looking at the DS1307 Real Time Clock chip that we've got here. I built it up onto a breadboard and we had a little play around with that square wave output. What I want to do this time is make that a little bit more of a permanent solution and solder all the components onto these circuit boards. I've had these made up by JLC PCB. I designed them in EasyEDA. We'll take a look at that in a sec. Had them manufactured and they have arrived, so I may as well go ahead and solder them on. As you can see, I've got plenty of these, far more than I need. I always order this many because JLC PCB charge you the same price for a 100 by 100 millimeter panel, so you can put as many circuit boards into that space as you want. So I always just fill it up because you pay the same regardless. But as you can see, I've got loads, so if anybody's interested in getting one of these boards, then make sure you leave us a comment below. So when you're designing a circuit board in EasyEDA, the first thing you want to do is create a schematic. You don't want to jump straight to trying to design the board. You want to draw up your schematic first. It's going to make life so much easier. I'm not going to sort of show you how I've done all of this. I'll just basically talk you through a few things. I've got my DS1307 in the middle here. You can see I've got the crystal connected on X1 and X2. There's my battery connected to VBAT and ground. I've got my 5 volt coming in here. I've decided to connect a 100 nanofarad capacitor. I think it mentioned that in the datasheet. I don't remember, but it's generally good practice to put a 100 nanofarad capacitor on the VCC pins of integrated circuits, so I've just included it. I've got a pull-up resistor pulling the square wave output line up to 5 volts. And these are called net ports. Anything that's connected to the net port with the same name is connected together. So this SQW will be connected to this SQW, and this SCL will be connected to this SCL, and this SDA is connected to this SDA. It just makes it easier and clearer to draw the diagrams. So I've then just got a breakout header here. I've got the 5 volts, serial clock, serial data, ground, and the square wave. And the reason I've got the ground sort of in the middle here like this is because I wanted to put the square wave on the end, because I generally won't be using that. So I'll be able to connect a 4-pin header across the first 4 pins, and I won't need to leave a gap for that missing pin. So then if we take a look at the PCB, we'll start with the top layer. So you can see the yellow is the silk screen, and you can see I've positioned the battery over here to the right, chip to the left. I've got my capacitor here connected to that VCC pin. I've got the pull-up resistor here. There's the crystal, and here's our breakout header. The only routing I've got on the top really is the 5 volt line coming in. I've made that trace slightly thicker than the others. That's 0.5mm thick. It goes to the capacitor and then to the VCC pin. So we want to keep the capacitor as close as possible to the VCC pin. Then I've also taken the 5 volt line over to this pull-up resistor, and then I've got this square wave output pin going down to this pin that I've marked as clock, or CLK. So that's all the routing on the top. On the bottom, I've got my crystal connected here, a line coming from the battery into the VBAT connection. We've got the SCL and SDA lines here, and then the pull-up resistor is going to the square wave pin. That's basically all of the routing. The only other thing I wanted to mention on here is I've actually created a break here in the ground plane around here, up here, and around the crystal. I've done that, so I mean I'm not really too sure what I'm doing here, but there shouldn't be any stray currents flowing through the ground plane and across the crystal that might cause some problems there. Now it does mention this in the data sheet. I don't know if I've interpreted it recommended layout for crystal. So there's they're showing the crystal basically connected right into the pins as close as possible, and they've got this area here which you can see on my PCB where they've marked it as a local ground plane. So I've interpreted that to meaning the ground plane in this area should be separate. I'm not sure if I'm totally understanding that correctly. And then it says avoid routing signal lines in the crosshatched area upper left quadrant of the package, and this is the crosshatched area. So we shouldn't be running any signal lines across here. There is a caveat, unless there's a ground plane between the signal line and the device. So you should hopefully see the crosshatched area would be this area here, and I've got no signal lines running across that area. So then we can take a quick look at the 2D view, and we get a 3D rendering. Hopefully it will render. Usually does. So it gives me an idea of what the thing should look like when I've built it. So I've connected it back up to the Arduino using some male to female headers. So I've got everything connected apart from the clock, the square wave, I should say. Now it will have lost its time because I disconnected the battery whilst we were doing that. So I've opened up the Arduino IDE and we should be able to just go straight to the serial monitor, and we can see it is still ticking away showing us the time, but obviously the time is now all messed up because we disconnected the battery. So I will have to just set this time again. So we're one day further forward. I've got 8 this time, that'll be 100 hours and 28 minutes. I'll upload that. Uploading, done uploading. Now I'm going to do it again with this commented out because we don't want the thing to keep resetting the time back to this every time we power up. So I'll upload again with it commented out. And then we should be able to go back to the serial monitor and see we've now got the correct time programmed back in. So that's good news, it's still working, assembled on the breadboard. The only thing I probably would change if I did another one of these, I've noticed I keep knocking this crystal and it is kind of fragile, it's bending over. It's kind of, I don't know if you can see that, it's kind of bent over and I keep pulling it back. I don't know how I keep knocking it, but it's obviously really fragile. So I think usually the way these are mounted are to lay it down flat with a bit of double-sided tape just to secure it. It gives it a lower profile and it's probably a little bit safer and more secure. So the only other thing I want to look at on this is that user RAM that we get. So we should be able to store some settings in there and recall them back. So let's have a look at that. So I was going to attempt doing some live coding and I'm so glad I didn't because I made a complete mess of it. I actually caught myself out. I had a function here called RTC read, I think was the one that was giving me problems. When I originally wrote this function, I had it doing the BCD conversion all inside the RTC read function, which is fine if you're reading binary coded decimal values, but as I was just trying to store some arbitrary values in the RAM, I didn't need it doing a BCD conversion, so that really caught me out. So I've broken that out now, so RTC read just simply reads and returns the value. And then I've got a little utility function somewhere here called dec, which converts 2 times, I think that should say 2 times 4-bit BCD value to a 2-digit decimal. So I just broke it out so that I can call the read function without doing the BCD conversion. So what I did, I added some code to the setup function. Now you wouldn't normally do this in the setup function, it doesn't really make sense to do this here, but it's just an easy place to execute some code. I've got here a string with the words hello Arduino and an exclamation mark, and then I'm calling a new function called store string. This is where I want to store it, and that's the string that I want to store. So we'll have a look at that function in a second. Then I'm storing an 8-bit integer value. So I've got an 8-bit integer and I've set the value to 255, and I'm calling this function store int 8. That is where I want to store it, and that is the value I want to store, which will be 255. And then finally I'm storing a 16-bit integer. I've just set it to some sort of arbitrary value here, and I'm calling this function store int 16. This is where I'm going to store it, and that's the value I'm going to store. Now I need to be careful, I'm storing 3 pieces of data in 3 different addresses, 0x8, 0x1c and 0x1d. I just needed to be careful that they don't overwrite each other, they don't overlap. So I've made sure I've left enough space that I could store all 3 and they won't interfere with each other. And then finally I'm dumping out all the RAM. Just got a for loop here going from 1 to 56, and I'm just doing serial prints. I'm printing out the address, which is going to be 0x7 plus I, plus however many we've counted in our loop. So it'll actually start at 8, and I believe it counts up to 3F, hexadecimal 3F. printing a full colon. Then I'm doing the RTC read from the address 0x7 plus I, which is the value we're at in our loop. And I'm serial printing it out as hexadecimal. I'm then kind of got another separator in there, another full colon, and then I'm doing the read again. A bit wasteful to do the same read twice. And that is just printing out is a decimal value. If you don't specify a second argument, you just get decimal value. And then finally, I've got another separator, and I'm actually casting it here to a char, and then printing that out. I'm doing the RTC read 3 times, which is a bit wasteful, but hey. So if I upload this, it should store these 3 values. Let's have a quick look at these functions. I didn't look at those, did I? So here's those 3 functions: store string, store int 8, store int 16. They all take 2 arguments. The first argument is the address of the register that you want to store to. And the second argument is the value that you want to store. In this case, it's a string. So I'm just grabbing the length of the string, int len equals str.length. Then I'm just doing a for loop, looping over every character in the string, and for every character I do an RTC write, reg plus I, and then I'm doing str.charat, so it just grabs the character at the index I and stores it in reg plus I. Hopefully that makes sense. The next one, store int 8. I've got some debug code here, let's get rid of that. This is the simplest one because you can just store it straight into the register, RTC write reg, and then just pass in the value. And then store int 16, slightly more complicated because we can only store, each memory location can only store an 8-bit number. So we have to kind of split this up into 2 8-bit numbers. So I'm splitting it up into a low byte and a high byte. To get the low byte, we just take the 16-bit value and we do a bitwise AND with the number FF, and that will give us the low byte. And then to get the high byte, we just take the 16-bit value and shift it 8 bits to the right. Then we just write both of the bytes out. So I'm doing an RTC write reg, comma high. So I'm writing the high byte first, and then I'm doing an RTC write reg plus 1, and then the low byte. I believe that's called big endian when you store the high byte first. I think if you stored the low byte first, it would be little endian. You can choose to do whatever you want. You just have to remember when you're reading back the way it works. So if we run this, it should store the values in the memory, in the RAM, and then it should dump out all the RAM. If I run that, I'm not sure what's already in my serial monitor. Let's clear. What I'll do is I'll clear the output and then I'll reset the Arduino. We should get a nice clean output. So there we go. So you can see it's dumped all the RAM from 0x8 to 0x3f. It's mainly empty. I actually erased it. I went over the whole lot and set it all to 0. Just made it a little easier to see what was going on. And then you can see at location 8, that's this store string, location 8. Let's make this window a bit smaller. So at location 8 we've got our string. So there's location 8 and there's every character of our string. Hello, space, 32 is a space, Arduino, and an exclamation mark on the end, exactly as we wrote it out. So that worked. The next one was at 1C, 0x1C, which is here, 1C. And you can see it's got a hexadecimal value of FF, which is 255 in decimal. And I believe this symbol here just means it has no character representation. I believe that's what that means. It doesn't understand what it is, so it just gives you this backward front question mark. But the string representation is irrelevant. We're storing an integer. And then we've got our 16-bit number at 0x1d, which is the very next location. Now, these are the hexadecimal values and these are the decimal values. And remember, this is our high byte and this is our low byte. So I got my calculator out. I believe I've got the calculator here. And I'm working in decimal, base 10. So if we take our 48, and what we do is we shift it to the left 8 bits to the left, and that gives us 12288, and then we can just add the low byte, which is 247, 247 equals 12535, and if we have a look, that is the number we stored, 12535. So it is correctly storing a string, an 8-bit number and a 16-bit number into the RAM. Now, it says it's non-volatile. So if let's remove the code that's setting the values, because otherwise we'll just be setting them every time we power up, and we don't want that. This is why you wouldn't really do it in the setup function. So I've removed all of the code that's going to store the values. I'm going to re-upload that to the Arduino. Done uploading. I'll clear the output. We'll just reset the Arduino so we get a clean output. There it is. All the stuff is still there because we haven't powered down or anything. Yep, all the numbers are still there. Now what I'll do next is I will power off the Arduino. Let's just literally unplug it here. So that is now completely powered off. It is still running on the battery backup. And we should be able to power it back on again. And we should see on the serial monitor, we can see here all the values are still there. Now I believe, so hopefully that demonstrates that we can remove the power and not lose any of our values we stored in the RAM, which is why it's called non-volatile. But I believe if we did remove the battery, then I believe we would lose it. So let's try that. So I'll power off. I'll try and get this battery out. I'm not sure how easy that's going to be. Might need a little tool. Let's see if I can get that out of there. How am I going to remove that? That is really in there, isn't it? Here we go. So the battery is out. So the chip is now fully powered down because there's no voltage source here now anywhere. We've not got the main power supply and we've not got the battery. So that should be gone or erased or set to some random values, who knows. I'll put the battery back in. I don't think we need the battery, but I'll put it in. And we'll power back up. I'll clear my output. It's busy doing stuff. I'll clear the output and I'll reset the Arduino. We'll see what we get. It's actually all still there, which tells me that it really is non-volatile. Even without the battery, we still didn't lose any of the values. So that's kind of cool. So that's about it. That's all I'm going to do with the real-time clock module. If you enjoyed those couple of videos, then please leave me a comment. I always appreciate some feedback. If there's anything you want me to cover in addition on the DS1307, then again leave me a comment, let me know what you want to see, and also if you want to see me work with any other integrated circuits, again leave a comment, let me know what you're interested in. So thanks for watching, and I'll see you next time.